Hello everyone, welcome to the block 2 of 42991 Advanced Water and Wastewater Treatment subject. My name is Sherapunso and I'm the senior lecturer at the School of Civil and Environmental Engineering here at UTS. This year, because of the COVID-19 situation, we are delivering this subject in online mode. Given the nature of the initial design to be delivered in a block mode, it was not practical for us to deliver live online lecture for 1.5 days. So we are pre-recording this lecture and then making it available to the students in the Canvas. However, we will have a 1 hour of live consultation session on the 8th of May. I think it's Friday. And this will be an opportunity for you to ask any questions related to the block 2. Of course, it's not limited to that. You can contact me anytime through the email given here and make an appointment with me so that you can I can clarify to have an online session face-to-face through Zoom or any other means and clarify any issues that you may have, so I'm able to help you in any way possible. I look forward to making this subject as lively and as interesting, as enjoyable as possible for you, so that we can achieve the best learning outcomes and the best learning experience from this subject. And I hope all of you are doing well at home, whether you are in Australia or overseas in your home country. Please do follow the health guidelines and the whole health advisory of your respective government in terms of social distancing and personal hygiene, and please always try to stay safe from this deadly COVID-19 virus. Before I begin, I want to just briefly introduce myself a little bit more. I have a civil engineering background that I obtained from the Regional Engineering College in Surat, Gujarat in India. And after that I went to Bhutan, worked in the urban development and engineering services for about 7 years. During that time I was involved in many projects related to water supply, urban water supply, urban sewage management, solid waste management, and many other urban infrastructures projects. I joined UTS in 2005 to do Masters of Environmental Engineering, some similar to some of you guys as an international student. And after that master course, I went back to Bhutan, worked in the same department for 2 years, and I was heading the urban waste management section this time with many projects in hand. Then I returned to UTS in 2009 to do my PhD, completed my PhD in 2012, then I started working at UTS as a postdoctoral fellow for a few years, and then got the academic lectureship from 2018, and recently as a senior lecturer. So my research expertise, or you may say academic expertise, lies in the field of water and wastewater treatment, and including desalination, and especially using the membrane processes. That's one of the research that we do. In fact, we do a lot of research related to these areas, and including the fabrication of new membranes using new materials and development of new materials that is useful for water and wastewater treatment. So if you are interested to do PhD, please do let us know. That we can help you explore some of the available scholarships from UTS. Actually, I was also the coordinator of this subject for a couple of years. I handed over to Professor Hok Young Shun from this year, but I continue to share teaching with Leonard and Sean, and I will be teaching this block mode from this year. So these are the contents of the block 2, and are divided into 3 sessions. In session 1, session 2, and session 3. And in session 1, I'll be covering on water treatment processes. What are the various treatment processes involved in the treatment of surface water for potable purpose. And in session 2, I will be talking about the membrane processes that's used for water treatment and wastewater treatment. And module 3 will be about the wastewater treatment, basically covering the conventional activated sludge process and the membrane bioreactor, which is an advanced form of wastewater treatment. The video session may be long because of a lot of slides in each session, so I may have to divide each session into sometimes more than one video file. So please refer to the numbering carefully for the video files. So let's start with session 1, which is module 2A, the water treatment processes or technologies. This session covers different treatment processes or technologies involved for the surface water treatment, where and why these treatment processes or the unit treatment processes can be applied in a treatment trains in a water treatment plant. And by the end of this session, you should be able to understand in more details what are the treatment units required for the water treatment plant, including some of the design considerations and also some of the optional treatments required for problematic water sources. So before we start with the treatment processes, I just want to let you ask a question as to why the treatment is required. So I'm sure some of you know, but for the benefit of those and to recollect some of the studies that some of you may have done in undergraduate. So why the treatment of wastewater is required? Why the treatment is required? Why wastewater treatment is required? What are the treatment goals? So surface water comes from various sources. Of course, we have water coming from rivers, streams, lakes, groundwater, and so many other rainwater and so many other sources as well. But because they are in contact with the environment, it can contain a lot of contaminants in water and making it unpleasant in appearance, color, taste, and odor, and smell. So these contaminants may include in the form of suspended solids. It can maybe in the form of dissolved chemicals, dissolved solids, including gases. It can be heavy metals, dissolved organic matter, and so many different types of contaminants. So all these contaminants have to remove to make the water pleasant and safe for drinking purpose, right? So that's the reason why we need the water treatment, right? Now, why do we need to treat the wastewater? The wastewater is part of the water after we use. So it may be at home, generated from the home, maybe from the industries, from the office buildings, or many other institutions, right? So wastewater is the water which is being used. So which means when we use it, after using it, we contaminate them, right? It can contain a lot of organic matter. So coming from in the form of fishes coming from the toilets. And also maybe we use in the kitchen to wash the dishes, and a lot of organics comes from there. We may use a lot of chemicals at home for cleaning purposes, maybe dishwashing chemicals, maybe other cleaning chemicals, disinfectants maybe. So there's so many different types of chemicals are being used. All this becomes part of the wastewater, right? So this has to be removed, because if you don't remove this, then it can pollute the environment, right? So that's the reason why the treatment is required. And the other reason maybe that because of the requirement from the legislation, the government legislation, that your wastewater effluent, if you discharge, it must meet certain standard, that you in terms of certain parameters, maybe that your organic content must not exceed this amount of concentration. So we have to follow that guideline, right? So in order to meet this environmental legislation, we need to have the treatment processes. So basically, wastewater treatment involves removing all these pollutants present in the water after the use. As you know, or you may already know, any water treatment plant or wastewater treatment plant, they do not rely on a single treatment process. We need a series of different treatment processes that targeting different types of contaminants. This is because one treatment process is not effective in removing all the types of pollutants present in the water. Hence, the water or the wastewater treatment processes can be divided into three major groups or processes, group of processes. The physical process, biological process, and chemical processes. In physical process, we use simple physical forces such as gravitational forces, momentum, pressure, etc. to remove pollutants from the water. A physical treatment process include mixing, flocculation, flotation, filtration, sedimentation, etc. The next is the chemical process. In this treatment approach, chemicals are used to remove pollutants or decompose pollutants or convert from one form of pollutants to the other form of pollutants so that they can be easily removed by physical means or physical process or biological process. So this includes treatment processes such as precipitation, coagulation, adsorption, oxidation, disinfection, decomposition, etc. So third and the last step of treatment process is the biological process. In this approach, the microorganisms play a significant role in the removal of or treatment of water from the water or the wastewater. Generally, the biological treatment processes are used mostly for the treatment of wastewater containing a large amount of dissolved organic matter as the major form of the pollutant. Although the biological activities does the job of removing the pollutants and treating the wastewater, however, the treatment mechanisms can also be associated with the combination of both physical and chemical process, but of course aided by the biological activities. This slide shows the water cycle of our human consumption. This water cycle is different from the natural water cycle that is present on the atmosphere on this earth. The water that we get from the various sources such as rivers, streams, lakes, etc. are first treated at the water treatment plant and make it potable for human consumption. So after the fresh water from the tap has been used, it is discharged as the wastewater from the users. So the wastewater is then collected and sent to the wastewater treatment plant, where they are subjected to a series of treatment processes before releasing back to the environment from where they came, thereby closing the water cycle. So of course, if a very high quality treatment is performed, then the treated wastewater can be used for non-potable purposes such as irrigation and car washing, cooling, etc. And this water reuse is nowadays becoming very popular because of the freshwater limited freshwater resources because of the climate change and the global warming that's impacting the climate. And reusing of the treated wastewater is in fact one way of significantly reducing the freshwater demand. This slide shows a typical treatment trend of a surface water treatment plant. A typical water treatment plant consists of several different types of processes, and additional process may be even required or necessary depending on the types of additional pollutants that may be present in water. So the first stage in the water treatment or wastewater treatment plant is the screening process to remove large matter that often comes with the surface water, such as in the rivers and lakes. The second process consists of a grit chamber to remove larger and set level particles with high specific gravity or density, such as gravels, sand particles, etc. The third process consists of a rapid mixing chamber where coagulant chemicals are dosed and subject to rapid flash mixing to enhance coagulation or mixing. So this process is followed by the flocculation chamber, where a slow mixing is applied to form a large particles of floc, to have aggregation of all the smaller flocks particles formed and let it so that it can settle easily by gravity. So the next stage after the coagulation and flocculation is the sedimentation tank, or also sometimes called as a clarification tank, to remove the larger particles, remove larger and heavier aggregated flocks by gravitation settling to the bottom. A clearer water or the supernatant is then passed to the next stage for the filtration. So filtration stage consists of a filtration bed, usually made of rapid sand filtration or slow sand filtration, made of single media or multimedia types of filter media, to remove any unsettled or smaller flock particles or the suspended particles that are not from as a flock. The last stage is usually the disinfection to kill the microorganisms present in the water, maybe in the form of fecal coliform, bacterial microorganisms such as including Cryptosporidium. So after the disinfection, the treated water, which is clean and safe, is then supplied to the drinking purposes to the household and other use. This slide shows an animated form of surface water treatment trains in a typical surface water treatment plant. This is similar to the one that I've shown earlier in the slide. Here you'll see the animations and also the points at which processes the chemicals are also added. So this slide shows a typical conventional wastewater treatment plant. The treatment train that you'll see in the wastewater treatment plant is a bit different from the surface water treatment plant that we have seen earlier. The most notable difference that you'll see is the existence of the primary and the secondary treatment units in a wastewater treatment plant. These treatment units are required, basically the biological treatment process for the removal of the large amount of organic matter present in the wastewater. So it can be formed in the various form. Organics can be in the various form. It can be in the settleable organic solids, or in the suspended solids, or also in a dissolved organic matter. So wastewater treatment plant also produces large amount of organic sludge, which require further treatment through the use of sludge digester that helps the microorganisms to convert the organics into methane or energy, and also biosolids, which can be further finally used as a soil conditioners. So of course we will be talking more about the wastewater treatment process in session 3. So from here on we will be talking individual process or treatment units separately. First comes the screening process. Okay, the screening is the process of removing large objects present in the water. It can be in the form of rags, large plastic objects, timber, branches, twigs, metal objects, and many other floating objects maybe that can be subtle also. So if they are not removed, they would cause damage to the pumps and also cause blocking of the pipelines at the wastewater treatment plant or the water treatment plants. So screening is the first treatment unit in any water treatment plant or the wastewater treatment plant, because the main objective is to first remove the largest particles or the largest object matter present in the water. A screen can be of several types, but mainly as a coarse screen or fine screen, depending on the size of the opening. Sometimes the screens are also associated with commutators that grinds or pulverizes the large objects into smaller particles that can pass through the thing, and also they can be easily separated. The next treatment unit in a water treatment plant is the grit removal or the grit chamber. So surface water, especially if the water is coming from the running rivers and streams, it can contain a lot of particles, heavy particles with high specific density and gravity that are not removed by the screening unit. So these heavier particles are termed as grit, and they can consist of particles such as sand, gravels that are not removed by screen bars, cinders, eggshells, bones, chips, so many the inert particles. So the second stage of the surface water treatment plant is usually the grit chamber to remove this grit from the surface water. Grit chambers are basins to remove these inner particles and prevent damage to the pumps, and also to prevent their accumulation in the sludge digesters. So the design of the grit chambers involve reducing the flow velocity of the water to allow settling of the only grit particles in the water. So grit particles are subjected to two types of velocities: horizontal velocity due to the flow of the water, and the settling velocity of the particle due to the gravitational weight of the particle, size and weight of the particles. So lowering the horizontal flow velocity increases the residence times of the particle in the grit chamber, thereby allowing enough time for the particles to settle at the bottom of the grit chamber and then be removed. There are three types of grit chambers: horizontal flow type of grit chambers, which can be rectangular or square shape; aerated grit chambers; and the vortex type of grit chambers. Both are in the form of circular shape. In the aerated grit chamber, an aerated grit chamber consists of a spiral flow aeration tank provided with air diffusion tubes placed on this one side of the tank. So the grit particles tend to settle to the bottom of the tank depending on the particle size and the bottom velocity of the roll of the spiral flow. So the bottom velocity of the spiral flow is controlled by the rate of the air diffusion through the diffuser tubes. So the heavier particles settle down, whereas the larger and the lighter organic particles are carried into the roll of the spiral motion. The chamber can also be either mechanically cleaned or manually cleaned. Horizontal grit chamber is the most common types of grit chambers used worldwide, because they are simple in design, and also they are much cheaper in construction and operation compared to the aerated or vortex types of grit chambers. So this table shows the design guides of the horizontal grit chamber. You'll see that the design parameters include the detention time, the residence time of the water in the chamber. The residence times will depend on the horizontal flow rate of the water, grit chamber cross-sectional area, and the horizontal flow velocity. So the approximate settling velocity of the particles depending on the sizes are also provided as a guide. When you design a grit chamber, the elevation of the grit chamber with respect to the successive treatment units should also be considered, since there can be some head loss in the grit chamber, especially if the water treatment plant is designed based on the gravitational flow. Okay, the next process or the treatment unit, is the aeration or the oxidation. But this is not found in a typical water treatment plant, but it's optional treatment, and it's basically applied if the water contains problematic components such as that causes taste and color in the water. So usually aeration is adopted by a small water treatment plants with very low flow rates, and it's not usually present in a large water treatment plants. In this aeration, the air is supplied to the water using air diffuser aeration, or sometimes water itself can be sprayed in the air. We call it dripping. So basically, we try to provide oxygen to the waters to have a contact with the contaminants. So the removal mechanisms by aeration involve two types: scrubbing action and the oxidation action. The mechanisms. So most dissolved gases are in fact removed by scrubbing action during the aeration. So it just scrubs the gases present in the water, by the providing oxygen. In the other mechanism, it's called oxidation. So it actually, in fact, oxidizes in the presence of oxygen. Then contaminants can be converted into another form of the compound. So, for example, maybe in the form of solid or precipitates that can be easily settle and separate out from the water. So aeration is applied to remove color from the water. So usually groundwater, for example, contains a lot of iron and manganese. So this manganese, they can cause color, so for unpleasant color in water. For example, iron can cause reddish color water, whereas manganese can cause dark brown or black color in water. So they have to be removed because it creates very unpleasant appearance of the water. So removal is usually recommended if the iron content in water is more than 0.3 milligram per liter and manganese more than 0.05 milligram per liter. So or the combined manganese and iron should not be higher than 0.2, and if it exceeds that, you have to provide aeration to remove this. So this chemical formula shows how the ferrous is reacts with oxygen in the presence of water to form ferric hydroxide, right, which is a solid from a precipitate and then can be removed from the water. Likewise, in manganese also reacts with oxygen and water to form manganese oxide, and then this precipitates can be removed from the water by either settling or for filtration. Aeration is also effective in removing hydrogen sulfide that causes odor in the odor problem in water, right? So hydrogen sulfide, it causes the rotten egg smell. It's very unpleasant smell. So if it is present in water, then yeah, the aeration is effective in removing this the hydrogen sulfide. So hydrogen sulfide, if the concentration is less than 2 milligram per liter, usually aeration is effective in removing the odor. But if its concentration exceeds 75 milligram per liter, aeration is not that effective. So chlorination may be applied here to remove the hydrogen sulfide from the water. So volatile organic compound is another unpleasant smell and taste that it can provide. So it has to be removed and can be removed by aeration. So volatile organic compounds or VOCs such as benzene, trichloroethylene, dichloroethylene, perchloroethylene, and various chemicals that causes taste and odors in water can be removed by the aeration. So if aeration is usually recommended when the volatile organic compounds are present in water. So the taste and odor caused by these gases such as hydrogen sulfide and also volatile organic compounds, they can be removed by a scrubbing mechanism during the aeration. There could be many other gases as well that is present in water that can cause this can be problematic to the water treatment plant, even if it is not the smell or the odor. So for example, carbon dioxide, if the concentration of carbon dioxide is high in water, then it can lead to the formation of carbonic acids, and this carbonic acid is is a weak acid, but can cause a problem in the form of corrosion, even the pipelines, pumps, and other accessories in the treatment plant. So aeration can remove the carbon dioxide present in water if it is in excessive concentrations. Methane is also another gas that's sometimes present in water, depending on the different sources of water. So it can also give an odor problem. So aeration is one way of reducing removing the methane present in the water. So carbon dioxide and methane are basically removed by the scrubbing mechanisms during the aeration process. So besides aeration, and oxidation, there are some other oxidation methods that can remove similarly to aeration process. So chlorination and addition of potassium permanganate is one way of removing or inorganics that causes color in water and also taste and odor from in the water. So because chlorination and potassium permanganate are very strong oxidizing agents, so they can oxidize the those problematic contaminants present in water. So action similar to the aeration process. Air stripping is another form of providing oxygen in the water to remove the contaminants that's problematic for water. So in aeration that we covered earlier, it is the process of dissolving oxygen in the water to react with contaminants such as iron, manganese, or also scrubbing action to remove the gases that causes odor, including hydrogen gases, carbon dioxide, methane, etc. But air stripping is the process of transferring the water component or the liquid component, so containing these volatile compounds, into the air streams. So basically, you're spraying the water containing these contaminants and bringing it in contact with the air. So in the aeration process, of course, in also a small amount of air stripping happens, but it's not enough or significant. So in air stripping process, the water becomes very much saturated with oxygen and it provides a significant amount of aeration. So that means air stripping is much more efficient in providing oxygen rich to the contaminants in water. So air stripping is not a cost-effective way of providing aeration alone, of course, but aeration is very inefficient way to remove volatile compounds. So combination or applying correctly the air strippers in aeration can be a very effective, very cost-effective way and a powerful processes for providing rich oxygen to remove the problematic components in water. So therefore, air stripping is the technology used for the purification of water containing high volatile compounds. Volatile compounds have relatively very high vapor pressure and low aqueous solubility, and they are characterized by dimensionless Henry's law coefficient. So this explains the mechanism of how the gaseous volatile compounds can be removed from the water by air stripping method. So Henry's law coefficient is nothing but the ratio of the concentration in air that is in equilibrium concentration in water. So I'm talking about the concentration of the contaminants or volatile compounds in water. So contaminants with relatively high Henry's law coefficients can be economically stripped from the water by air stripping method. So that's the reason why we apply this air stripping method to remove the volatile compounds, because they have high Henry coefficient law. So these contaminants containing high Henry's law coefficient include BTEX compounds such as benzene, toluene, ethyl benzene, and xylene that's usually found in gasoline, and also the solvents including trihalomethane, trichloroethylene, and tetrachloroethylene. So these compounds are usually found in countries or the regions with that has rich that is associated with oil reserves. Ammonia can also be stripped from the wastewater by a stripping method. Ammonia is also a volatile compound. So And they can, because of that, they have high Henry's law coefficients, and that therefore can be easily removed by the air stripping method. Because ammonia in wastewater effluent is toxic to the environment and needs to be removed. Of course, in the conventional wastewater treatment plant, the aeration process, the activated sludge process that involves aeration, removes this ammonia. Basically ammonia, converting ammonia into ammonium into nitrate by nitrification process, and then nitrate after is formed into nitrate. Then nitrate is again further processed to denitrify to form nitrogen gas. If the temperature of the water is warmer or warmer temperature, Henry's law coefficient also increases with the temperature of the water. So striping becomes more effective at warmer temperature. So this next unit is the coagulation and flocculation unit. After the large matter and the grids are removed, the water will contain a lot of colloidal particles or suspended solids that are not removed by the screen and the grid removal units. So suspended solids or the colloidal particles are micro-sized particles, and they have very low settling velocity, as you can see from this table here. So it takes very long time for them to settle, depending on the smaller the particle size, higher it equals longer period to settle down. So it becomes impractical to use the gravitational settling method to remove these particles, suspended particles, because it requires very light, high retention time, and this means it requires very large settling basins. Besides the suspended particles, suspended solid particles also have net negative surface charge in water, and that promotes electrostatic repulsion between the particles, that keeping them from suspension. And besides, and this is also aided by their Brownian motion, still keep them from moving from one another to another, not settling down. So turbidity is the measurement used as one of the indicators for the colloidal particles in or suspended solids in water. So turbidity in fact measures the cloudiness of the water, and for potable water, turbidity is potable water should be less than 7.5 NTU, and generally it is recommended to be less than 0.1 NTU. So if the suspended solids or these colloidal particles cannot be settled down, we must have some means to remove this. So coagulation is and flocculation is the process of removing the suspended solids from the water. So coagulation is the process of destabilizing of the colloidal particles or the suspended solids by addition of chemicals that neutralize the negative charge of the particles. So coagulation is actually essentially a chemical process, because you add chemical to the water. And flocculation is the physical agglomeration of destabilized particles to form a larger size aggregates known as flocks, which can be effectively removed by sedimentation or flotation. So during the coagulation process, it's what happens is smaller flocks are formed because the charge is neutralized. When the charge are neutralized, then these particles, the suspended particles, very minor particles, will agglomerate and join together. So when they join together, it becomes a little larger flock, and then flocculation further aids in agglomerating this the smaller flocks, and then forming a larger aggregates which becomes heavy enough to settle down or to be removed by flotation. So coagulation and flocculation therefore removes colloidal or suspended particles of 0.001 micrometer to 1 micrometer range. It also removes phosphorus and certain amount of organic matter, dissolved organic matter in BOD and COD, and microorganisms is also in water, because microorganisms are also negatively charged, so they can also aggregate each other and then form a larger flux and remove together with the flux. So coagulant, or sometimes it's called flocculant. So coagulant is the chemicals used for the destabilization of the colloids or the suspended particle solids. So chemicals used as coagulants include alum or aluminum sulfate, polyaluminum chloride, ferric chloride, ferric sulfate, polymers, and some other novel coagulants that has been recently developed and yet to be commercialized. And how they are removed. So from this equation it can be clear. You'll see that if alum is used, for example, the alum gives lots of different species in water when it's in water, so they dissociate from so many different species. So you'll see that Al3 plus is formed here and sulfate is formed there. So this Al3 plus is responsible for neutralizing the charge of the negatively charged suspended solids. So the suspended solids which is negatively charged will come towards the Al3, aluminum 3 plus, and then agglomerate each other and then neutralize. And when they neutralize, then there's no more electrostatic repulsion. So when there's no electrostatic repulsion, then when there's a Brownian motion, during the Brownian motion they will collide each other, and then larger aggregates are formed, and then they will settle down after making it a larger flux. So this is called charge neutralization. So this is the mechanism of how the flux is formed, and larger flux are formed, flocculation, and then it's removed. So there are two steps involved in the coagulation flocculation unit. The first is the rapid mixing. Actually, this is the coagulation step. So the retention time of this rapid mixing is around 10 to 30 seconds only. So this is the process of destabilization or charge neutralization, or is the coagulation process. And where rapid mixing is at very high speed, the chemical, the coagulant is mixed with the water. The next step is the slow mixing. So this in this unit, what happens is the pedal unit rotate very slowly, okay, very slowly, or usually less than 1 RPM. So velocity that creates a flow velocity of water at around 15 to 50 centimeter per second. So with a detention time of around 15 to 40 minutes. So in this process, very much larger floc aggregations occur and becomes heavier, and then they can settle it easily. Of course, we require optimum dosing of the flocculant or chemicals is very crucial, because if you add too much, then it can not only sometimes lead to low aggregation of the low removal efficiency, but also is a wastage of the chemicals, and also that the residual chemicals may also have health implications. So that's why optimum dosing of a flocculant or coagulant chemical is very crucial. So usually the jar test is usually performed, so where to determine the optimum dose of the coagulants. For example, you can have this many different types of in this many different jars, same volume of water, and then same mixing you can achieve with thing, and then but you can dose different types of the concentrations of chemicals, the coagulants here, and then see which gives the highest flock formation. So this is how you try to achieve the optimum dosing of the coagulants. So optimum dosing is very important for coagulant because excess dosing could impact the downstream treatment processes, and also it can have a long term if there's a long term exposure to residual alum, for example, in drinking water, it can accumulate in the brain and cause neurodegenerative diseases such as Alzheimer's disease, dementia, Parkinson's disease, etc. So this has been proven, and that's why in some countries alum is not used anymore as a coagulant. So they in that in the place of alum, ferric based coagulant is used, and also polymer based coagulants are used. And if you use too much alum, also it can produce a lot of sludge, and the sludge disposal is a big challenge because it has to be sent to the landfill site. And because of all these issues, nowadays people are working, doing research to find and investigate new novel types of coagulants where to address some of the problems. Yes, the first problem to address is that you produce less sludge, and then the sludge can be recycled to form useful products, and that the residual coagulant is less toxic to humans after consumption. So these are some of the novel ideas, novel ideas of developing new coagulants. Our group, led by Professor Ho Kyung-Shon, has done quite a work on the development of novel coagulants, and that can be recycled to form useful products. And so the example is the titanium-based coagulant. So titanium chloride, titanium sulfate, polytitanium chloride, and polytitanium sulfate. So these are some of the examples of the novel coagulants being recently investigated by our group. And because of course the titanium based coagulants are quite expensive, but the advantage of using this is that titanium based coagulants can have lot of different species in water, and because of that the charge neutralization is very effective because they are multivalent cations, and the most useful the most advantage is the ability of the sludge to be converted into titanium dioxide, which is a very useful photosynthetic materials, nanoparticles. So when after the coagulation, the sludge is burnt, and when after burning the sludge, the residual products that you get and grinding, you get a titanium dioxide powder. So this titanium dioxide powder can be used, has many wide range of applications, environmental applications. You can use in cosmetics, it's used as a surface disinfectants, as a photosynthetic material. So many different applications are there. So this is one of the research works being done, led by Professor Ho Kyung-Shon at UTS. Okay, let's talk about the design of the coagulation and flocculation tank. So let's first talk about the coagulation tank or the design of the rapid mixing tank. So these are some of the criteria that we will be using. We'll be using the mixing time. Usually it is around 30 to 60 seconds use, and based on this mixing time you can determine the dimensions of the mixing tank. So you can find the volume, width and height, depending. Sometimes the width and height ratios are usually given. Now the next thing is to calculate the power requirement for the rapid mixing, because you have to design the motor for the mixing, right? So how do we determine the power? So to determine the power, the following equation below can be used, which is a function of the velocity gradient g and the the volume of the tank and the viscosity of the fluid. So g is nothing but the velocity gradient, which actually it gives the degree of mixing. So G values should be between 700 and 1000 per second for a rapid mixer with a mixing time of around 30 to 60 seconds. But G value, if we want to do inline mixing, instead of having a separate mixing rapid mixing tank, you can also mix inline through the pipeline. So if you do that, then you can have you can assume the G to be around 3000 to 5000 per second, and a very short mixing time of 1 to 2 seconds only. So next is the design of the flocculation tank or the slow mixing tank. While doing this, you can use a detention time or the mixing of around 20 to 60 minutes, and based on that you can now determine the dimensions of the tank volume, width and height, and the G values of the flocculation should be around 20 to 80 per second, and typically the G into T, so G into time, should be within the range of 2 into 10 to the power 4 and 10 to the power 5. Why this is why we give these ranges? Because if you have a larger G and a smaller T, the problem is that you will have a dense floc but very smaller flocks, particles will be formed. But if you have a smaller G, which means small slow mixing, very slow mixing, but a very longer time mixing, then this gives you a very large flock size but not very dense flock, so it can not settle easily. So we need to have a balance. We need to have a larger flock and heavier, which is denser flock, to be able to. Sometimes this can be achieved by designing a flocculator with different G values. So the same equation can be used for the design of the flocculation tank. Once the water is passed through the coagulation and flocculation tank, then it is sent to the sedimentation tank. So in the flocculation tank, the smaller floc particles that are formed aggregate to form larger flocs and heavier flocs, and then when they reach the settling tank, the suspended solids or these aggregated particles, they are allowed to settle by gravity and then removed from the water. So how they do is by designing in such a way that the water velocity in the settling tank is lowered below the suspension velocity of the particles, and this allows enough time for the aggregate particles to settle at the bottom by the gravity and they are removed. So this process is also sometimes called as clarification or settling tank, settling or sedimentations. And of course gravitational settling because of the formation of larger floc particles is one way of settling, but there are also other mechanisms involved in the removal in the sedimentation tanks. What happens is this flocculation is caused by the different settling velocity of the particles, and when they settle, these heavier particles overtake and lighter overtake the lighter particles, and they coalesce, and they coalescing each other, means they aggregating each other and then forming larger and then they settle at the bottom. So in fact, this clarification or the sedimentation could remove up to 90% of the suspended particles from the water. So it can even remove the bacteria and thereby reducing the load going to the filtration unit. Sedimentation unit may not be necessary sometimes, especially if the water has low turbidity, turbidity less than 10 NTU. In this case, what you can do is you can avoid the need for a sedimentation tank, and then instead away take the water from flocculation tank to the sand filtration bed. And the sedimentation tank can be designed as a rectangular tank, and which is one of the simplest form of design, and they are quite cost effective, have low maintenance cost, but the disadvantage is that they require a very large area because it's very long length. So usually in most cases it is the circular sedimentation tank is usually the most preferred sedimentation tank that you will see in most most water treatment plant and wastewater treatment plant. Sometimes square sedimentation tanks are also provided. So the sedimentation tanks can also have a scraper at the bottom to remove this sediment, the whatever is settled at the bottom. So these are some of the design criteria for the sedimentation tank. This table provides some of the range of values that you can consider for designing the circular sedimentation tank. So what you require is the detention time, how long the water has to be in the sedimentation tank. Usually this range are given, and based on that you can find the volume of the sedimentation tank, and sometimes the height of the range of the height that you can provide is also given, and based on that you can find the surface area of the tank, or sometimes with the width or length ratio of the sedimentation tank is also given if you are designing rectangular or the square sedimentation tank. And the height of the sedimentation tanks usually recommended between 3 meters and 3.6 meters, and based on this design guidelines you can design the sedimentation tank. So next stage of the water treatment plant is the filtration unit. The water coming from the sedimentation tank still contains about 10% of the suspended solids. So the objective of the filtration is to remove those suspended solids and the floc particles that are too small to be effectively removed by the sedimentation tank. So, but the filtration removes the suspended solids or the small floc particles by physical straining, sieving, settling, and absorption within the filter media. So in fact the filtration can remove up to 99.5% of the suspended solids that's coming from the suspended solid of the water coming from the sedimentation tank. In the filtered water after the filtration can be less than 0.5 NTU of turbidity, but the desirable is less than 0.1 NTU. So nowadays the filtration is a must in most water treatment plant, because the turbidity can be a problematic because the microorganisms growing in the suspended solid is hard to be killed by the chlorine disinfection, and sometimes the colloidal particles themselves use up a lot of chlorine and affecting the residual chlorine. If 99.9% of Giardia cyst and 99.99% of the virus is to be removed from the water as required by the drinking water standard, then low water turbidity is highly desirable, of less than 0. NTU or less than 0.12 in the NTU, and therefore sometimes turbidity is used as an indicator of the presence of Giardia cyst and the viruses as well. For the design of the filtration unit, the type of filter media and the size are quite important. The types of filter media can be single media, like such as SEN, or dual media, anthracite coal and SEN, or multimedia is a mixture of 3 different or more than 3 different types of media, filter media. So dual or the multimedia filter is more effective because sometimes it can potentially remove some other problematic pollutants present in water by absorption. And as particles are removed by this filtration, the particles deposits on the sand surface can then the filter media surface and then get clogged, and it can result in the head loss. And because of this, sometimes the turbidity can also increase in the filtered water. So in order to solve this problem, the filter has to be backwashed. So backwashing involves forcing water in reverse direction of the filtration to dislodge all these deposited particles from the filter media. It's usually done once a day, and it takes about 10 to 15 minutes, and this is done using clean water usually stored in the overhead tank. So the dirt is then scraped from the surface of the top surface of the filter, and then sometimes replaced with the thin layer of the additional filter media. So you must have at least 2 filter media in any water treatment plant, because when one filter media is under maintenance or under backwashing mode, then the other filter media as other filtration tank has to be in operation for continuous water supply. For the design of the filtration unit, surface loading is the important parameter that we need to consider. So surface loading relates to the what amount of water flow rate that you can apply in a square meter of the filter area. So for slow sand filter, it is between 2.9 and 7.6 meter cube per day per meter square. So which means if you have water treatment capacity of 2.9 meter cube per day, then you need 1 square meter of filter area. So for rapid sand filter is much more. It's 120 to 300 meter cube per day per meter square. So as I said earlier, I think normally we need to construct at least 2, and usually the filter media is designed as an even number. So, and the surface area of each filter should be less than 100 square meter. And so if you have say for example 300 square meter of filter media required, then it's better to provide around 4 numbers of filter media. The next process in a water treatment plant is adsorption. This is an optional treatment because you don't find in this process in a typical water treatment plant, but they are applied usually for removing the problematic compounds present in water, or problematic contaminants present in water. especially if they are present in very low concentration or is in trace concentration. So adsorption is the process of additions of atoms or ions or molecules of gas, liquids or dissolved solids on the surface of the absorbent. So what it does is basically a surface phenomenon. The adsorbent, it can be a natural absorbent such as soil, sediments, etc., or it can be man-made, anthropogenic, like activated carbon, silica, etc. They provide a very large surface area, and the dissolved compounds or the dissolved contaminants in water can be removed by this adsorption. For example, the trace compounds such as pesticides, heavy metals, pharmaceutical compounds, personal care products, they are hard to be removed by the filtration and the coagulation. So if you must remove from the water, the adsorption is the effective way of removing from the water. So the absorption also remove taste and odor from the water, also chlorination byproducts, disinfection byproducts, and also nutrients such as phosphorus and nitrogen from the water. The theoretical absorption capacity of the absorption can be absorbent can be described by adsorption isotherm. I'm sure you must have some of you must have learned this in chemistry in the high school and also in undergraduate. So there are two types of isotherm: Langmuir isotherm, BD isotherm, and Friendlich isotherm. So Friendlich isotherm is widely used in the water treatment. Actually, this isotherm shows a curve relating to the concentration of the solid on the surface of an absorbent to the concentration of the solid in the liquid which it is in contact with. So it's basically it gives you a kinetics of how the removal process happens from the water by using particular adsorbent. The next is the ion exchange process. Ion exchange is the process of exchanging ions between electrolytes or between an electrolyte solution and a complex. Ion exchange is an optional treatment unit and is not found in a typical water treatment plant. Ion exchange is sometimes used for treating hard water. So hard water is caused because of the presence of excess calcium and magnesium in the water, and the ion exchange is one of the processes used for removing excess calcium magnesium from the water. This figure on the left shows this figure on the left shows the ion exchange processes. It has two stages, two processes: softening process and the recharge process. So after the softening process, then ion exchange has to be recharged. So there's one cycle. So softening and recharge, softening and recharge. So in the softening, what happens is the hard water containing calcium and magnesium pass through the packed resin containing a lot of sodium ions attached to it. So the calcium and magnesium ions present in the water will be exchanged with sodium, and the water that comes out of the ion exchange tank will be containing more of a sodium and less of the calcium and magnesium, and making the water soft. But with time, the resins will get saturated, and now in the recharge process, what happens is that concentrated brine containing sodium will be passed through the resin, and the calcium and magnesium present in the resin will be exchanged with sodium this time, and then the waste that comes out from the ion exchange tank will be full of calcium and magnesium, and now the ion exchange is ready for the next cycle of softening. So in that way, the one cycle will consist of softening process and the recharge process, and in that continuously it works. But to have a continuous operation, usually there will be two ion exchange tanks. One will be working in the softening stage, while other will be working in the recharge stage. The last treatment unit in a water treatment plant is the disinfection. So the clean water coming from the filtration unit is subjected to disinfection before it is sent to the water supply system. The water used for drinking and cooking should be free from pathogenic organisms that can cause disease, right? So disease and illness such as typhoid, dysentery, cholera, gastritis are very common if the water is not properly disinfected. So the biological quality of the drinking water is determined by the test for coliform group of bacteria. This actually, the coliform is the found in the intestinal tract of warm-blooded animals and also in the soil. So their presence in the water indicates a pathogenic contamination, but they themselves are not considered to be pathogenic, but they are used. Therefore, the coliform bacteria is used as an indicator for the pathogens, and because they are easy to test and then survives longer, and they're less sensitive to disinfections. The standard for the coliform bacteria in the drinking water should be that it should be less than one coliform colony per 100 milliliters of the water. So the disinfection is the process of the partial destruction of a disease-causing organisms in the water, so making it the water safe for human consumptions. Of course, disinfection does not kill all the organisms or destroy all the organisms completely, as in the process of sterilization. So the clear water that is coming from the sand filtration with free of suspended slow solid is usually treated with the powerful oxidizing agent, either chlorine, chloramine, ozone, or any other disinfection chemicals. The primary objective of disinfection is to inactivate the microorganisms that is present in the water. The secondary objective of disinfection is to have a residual disinfect present in the water to prevent reinfection during the storage in the reservoirs, and also during the conveyance along the pipelines. However, for example, if you use chlorine as a disinfectant, it can also produce some harmful byproducts such as trihalomethanes or THMs, and these disinfection byproducts are suspected to have links to stomach cancer and miscarriages. So disinfection has four mechanisms how they inactivate the microorganisms present in the water. The first mechanism is the damage to the cell wall, or they call it cell lysis and death of the microorganisms. So this is how the disinfection can probably kill the bacteria. The second mechanism is the alteration of the cell permeability. So it destroys the cell permeability, or the selectivity, and in that process the microorganisms become ineffective. It also can alter the colloidal nature of the protoplasm, making the microorganisms inactive. The last one is inhibition or deactivation of the enzyme activities of the microorganisms and may rendering them ineffective to cause harm to the human consumption. So, but there are many factors influencing the effectiveness of the disinfection. This includes contact time between the disinfectant and the water, the types of disinfection chemicals used, and the concentration used can also determine the effectiveness of the disinfection. The pH and also pH and the temperature of the water also plays important role in the effectiveness of the temperature of effectiveness of the disinfection. So at this ideal pH or the optimum pH, the some disinfectant can be very effective. And the types of organisms and the number of organisms present in water can also determine the effectiveness of the disinfection. And also the nature and composition of the water also can be affect the effectiveness of the disinfection. So this table shows the removal or the destruction of bacteria by different processes. You will see that chlorination is the most effective in removing the bacteria from the water compared to many other treatments. So the table, the figure on the right shows the log survival of the microorganisms at the different the exposure time, contact time, and the with different concentrations. For example, if you use very high concentration of chlorine, for example 6.04 gram per liter, then it requires very less time, say around how much less than around 100 100 minutes, right? Like 100 minutes to have almost complete removal of the microorganisms. If you use lower concentration, for example 4.62 gram per liter, it takes longer time to inactivate the microorganism. So if you look at here, if you use quite low concentration 3.48 gram, it requires very long time to deactivate. So the contact time and the concentration plays an important role. So these are some of the commonly used disinfectants, and you will see that chlorine, ozone, UV light, chlorine dioxide, and chloramines are some of the commonly used disinfectants. But chlorine is the most widely used. They are cheap and they can be used in many stages of the water treatment plant or the wastewater treatment plant. So it is appropriate for both primary and the secondary disinfectants. But they also produce a lot of harmful disinfection byproducts, halogenated ones. So they can also cause corrosion, increase the pH, and also cause corrosion in the pipelines when used as a secondary disinfectant. So ozone is a very effective, highly effective to disinfect, but also produce minimal harmful byproducts. But the problem is that they are relatively high in cost, and the operation is also more complex, and they cannot provide a residual disinfectant because their half-life is very short. UV is another effective disinfection for virus and bacteria. It can be easily set up and no harmful residuals or byproducts are formed. They are simple in operation and maintenance, but they are not very appropriate for water with high suspended solids, because if the turbidity is high, then the UV will not be very effective, and also they cannot provide the residual disinfectant. Chlorine dioxide and chloramines are the relatively cheaper way of doing, but they are less. They're not that effective as the chlorine and the ozone. Okay, let's talk about the chlorine disinfection because they are one of the most commonly adopted disinfectant in the world. Chlorine, when dissolved in water, produces hypochlorous acid, hypochlorous HOCl, and hydrogen ions and the chloride ions. So, but depending on the pH of the water, this hypochlorous can convert into another hydrogen ions and chloride ions. But in fact, we want HOCl, the hypochlorous, because it is much more effective. In fact, 80 to 100 times more effective than hypochlorite for the disinfection of E. coli. So, but together with hypochlorous and hypochlorite, they are called free available chlorine. The hypochlorous reacts in the presence of ammonia in water to form monochloramine, dichloramine, and trichloramine. And this reaction, of course, depends on the pH, temperature, and contact time, and also the chlorine to ammonia ratio present in the water. So all these monochloramine, dichloramine, and trichloramines are together called the combined available chlorine, and they do have disinfection properties, but they are not as strong as the HOCl and hypochlorous and hypochlorite. And you will see from this plot that the formation of the hypochlorous and hypochlorite is pH dependent. So if your pH is around 5.5, you will have the highest concentration of hypochlorous. Then it becomes, so which means ideally, if your pH of the water is around this 5.5, the chlorine disinfection will be very effective and very effective and efficient, because it produces the highest hypochlorous concentration. But if the pH increases above 5.5, say if it's around 7, then it contains equal concentration of hypochlorous and hypochlorite species. So yeah, so they are a bit less effective. So the pH, controlling pH is also important in the disinfection. This slide shows the breakpoint chlorination. So chlorine is a very strong oxidizing agent, so it can react with many compounds present in water, not only the microorganisms. Of course, our target is the microorganisms, but the chlorine is also used up reacting with other pollutants present in water. So this plot here shows the amount of chlorine added and the chlorine residue that's present in water. So we can divide it into different stages here. If you look at between points 0 and A here, how much ever you added, whatever you added chlorine here, there is no residual chlorine formed because all the chlorine you add in the water is used up for the destruction of for reducing compounds such as iron, manganese, hydrogen sulfate, organic matter, etc. So it reacts with them, and all the chlorine is used up. So between point A and B over here, the chlorine the combined residual increases. What happened here is that the the chlorine that's added reacts with ammonia to form chloramines. They're mainly monochloramines and dichloramines, and the combined together of these becomes the combined residual. So they increases here the previous the combined residual chlorine after the point B. After point B, if you continue to add chlorine, then the chlorine is used up to form trichloramines, and all the remaining chloramines are formed to go converted into nitrous oxide and nitrogen gas and chloride, and after the breakpoint B. So if you add further from here, then all the whatever you have the increases the free and the combined residual chlorine. So free residual chlorine increases from this point. So the point at which the free chlorine, residual chlorine increases is called the breakpoint chlorination. So this is the minimum chlorine concentration that you have to add to the water. So if you want to have no residual chlorine after disinfection, this is the breakpoint that you have to add. But if you want to have certain amount of chlorine present in water in the pipelines after disinfection as a residual free chlorine, then you have to add more this water. So this is the break. In ideal system, water supply system, the free chlorine should be at a concentration of 0.3 to 0.5 milligram per liter after a 10-minute of contact time. So chlorination levels. If a system sometimes a situation arises that such that it doesn't allow adequate contact time with the normal dosages of chlorine. In such cases, we do the superchlorination, and the superchlorination is the process of providing a very high concentration of chlorination to have very high concentration of residual chlorine, say from 3 to 5 milligram per liter, which is 10 times the recommended minimum breakpoint chlorine concentration. So because the retention time of the and the retention time of the superchlorination is around 5 minutes. But to have very high residual chlorine is not really recommended. So in order to bring the chlorination residual chlorine down to acceptable level, dechlorination has to be done before supplying the water. So the dechlorination process involves removal of total residual chlorine or the combined of free chlorine from water with the addition of sulfur dioxide or activated carbon or sodium sulfate or sodium metasulfate as an additional chemicals. So in order to reduce the toxicity of the residual chlorine on the downstream pipelines. And the superchlorination is usually used during the outbreak of the epidemic such as cholera, dysentery, and the waterborne diseases. So there are some other disinfectants that includes hypochlorite salts, which is sodium hypochlorite, and calcium hypochlorite, but they are not as effective as the oxidizing agent as the chlorine. And chlorine dioxide is another one. Ozone, of course, we have seen, but we already touched it. And ultraviolet radiation and S1 oxidation processes. But of course, we have already covered this one in the earlier session. The Australian Drinking Water Guidelines says that the chlorine in this water pipeline should not be more than 5 milligram per liter. This is the maximum that's permissible. Normally, the chlorine concentration in the drinking water pipeline should be ranging between 0.5 and 1.5 milligram per liter. So in fact, in the drinking water, if it's treated well by the coagulation and flocculation followed by filtration, 1 milligram of chlorine, 1 milligram per liter of chlorine for 30 minutes contact time is generally sufficient to reduce bacterial numbers. Of course, for the wastewater treatment, it requires up to from 20 to 40 milligram per liter of chlorine. So when chlorine is used as a disinfectant, there are also problem because disinfection byproducts are also formed. So when chlorine is added and if the water contains organic matter, especially the humic acid and fulvic acid, so this humic acid and fulvic acid are the natural organic matter that's coming they are dissolved in the water, in the surface water. So if because of their presence, it reacts with chlorine and forms what you call the trihalomethanes or THMs. So and then this disinfection byproducts was the first to be discovered as one of the DBPs, and they are formed during the chlorine disinfection or disinfection by chlorinated disinfectants. So the THM concentration is quite high in surface water than the groundwater, and also in summer the THM formation is higher than in winter because of the concentration of natural organic matter, and the temperature also plays a vital role in the THM formation. They are considered as a carcinogenic because they can also damage the liver, kidneys, and central nervous system. So that's the reason that in some countries they have a standard in which they state that the concentration of trihalomethanes or THM should not be exceeding these concentrations. I don't have the number here, but yeah, in United States they have a standard for the THM concentration. This THM can also be formed in the swimming pools where chlorine is used, or chlorine or the hypochlorite is used as the disinfectant, and when it reacts with urine, sweat, and skin particles that's coming from the people, then they can also form the THMs or disinfection byproducts. The next is the UV disinfection. UV is electromagnetic radiation at a wavelength of 100 to 400 nanometer can be very effective in denaturing the DNA of the microorganisms, thereby killing or inactivating the microorganisms present in water. The UV wavelength of 255 to 265 nanometer are the most effective in destroying DNA and RNA of the microorganism, and are the most lethal wavelengths for the UV disinfection. At 280 nanometer wavelengths, UV is able to denature proteins and enzymes as well. The quality of energy transmitted at a wavelength of 254 nanometer is usually the standard used for estimating the UV disinfection potential for any water. However, UV disinfection is seen as a very energy intensive process, and also the lamps are quite expensive. And UV is actually, in fact, the sunlight also provides, also contains a lot of UV. So UV from the sun, solar UV is also used as a disinfection. For example, if you have a solar pond, or what we call it the waste stabilization pond for the wastewater treatment, the solar ponds, these waste stabilization ponds, uses sunlight or the UV from the sunlight for disinfection. So this figure shows the UV setup, disinfection setup. So it involves the flow of water through this UV chamber or the vessel, which contains UV lamps. As the water passes through these UV lamps, the microorganisms are exposed to this intense UV light energy, and in the process it damages the DNA and the RNA needed for the reproductive functions, and therefore denaturing them and making them. However, if the UV is effective for disinfection, then it requires maintaining a minimum UV dose. So the UV dose can be calculated using this equation. It's a multiplication of UV intensity and the time of exposure. So you can do the calculations, and in minimum time of exposure is around 10 to 30 seconds. And to achieve or inactivate 99.9% of bacteria, this list shows what are the UV intensity or UV dose required. For example, for Aeromonas salmonixida, it requires 4 milliwatt second per meter square, and so forth. So this data can be used for calculating the UV dose or for the UV disinfection design. For UV disinfection to be effective, the water that is being treated by UV has to have very high transmittability, so which means the turbidity of the water has to be very low, less than 0.12 NTU. And if the turbidity is very high, then the UV disinfection is not very effective, because it will not transmit the UV and then rendering it ineffective. The next is the ozone disinfection. Do you know that the ozone is formed by natural process? There are two ways how ozone is formed in the atmosphere. The first one is the lightning, and it's also called coronal discharge. Lightning involves a high voltage. So when this high voltage or the current passes through the air, the oxygen present in the air is the oxygen molecule present in the air is broken down into elemental oxygen. And when these two elemental oxygen recombines, they form the ozone. And the other way is the UV light. The sunlight releases UV light. The UV light, especially the 185 nanometer wavelength, when it passes through the air, it also breaks down the oxygen molecule into elemental oxygen, and then recombine to form ozone. So these are the two methods how the ozone is formed in nature. So by adopting this approach, then we are able to engineer and create the generate ozone ourselves. For example, the coronal discharge, a high voltage is applied within the two plates, and when the air flows through the air containing oxygen flows through the plates, then the air is broken down into oxygen is broken down into elemental oxygen and recombined to form ozone. Similarly, the same UV light, UV approach can also be applied to form ozone. So the corona discharge method can generate very high ozone concentrations and best for applications. The ozone generation using UV light is more simple in construction and lower cost than corona discharge. So ozone is a very strong oxidizing agent. If you look at this table, the ozone ranks top amongst the list of the oxidizing agent. It has a very high oxidizing potential, much higher than any other the oxidizing agent. So it can directly oxidize, say for example, nitrite to nitrate. It also helps remove color and dissolve organic matter by breaking up the non-biodegradable compounds into smaller and more biodegradable compounds. It also helps in removing the dissolved and fine particulate matter in water, thereby enhancing the water treatment processes. And how ozone kills bacteria? The healthy bacillus bacterial cell wall is very important for bacteria because it ensures it ensures keeping the organisms maintain its shape and intact. But as the ozone molecules comes in contact with the cell wall, an oxidative burst occurs which creates a tiny hole in the cell wall, thereby injuring the bacteria. So this injured bacteria begins to lose its shape while more and more ozone molecules continue to create holes in the cell wall. As thousands of ozone collisions occur within a very few seconds, say typically 1 to 10 seconds, the bacterial wall can no longer remain a shape and then therefore the bacterial cell dies. This is how it typically occurs within 1 to 10 seconds, so it's very effective in killing the bacteria or disease. However, the ozone has some disadvantages as well. Ozone is a highly unstable molecule which can quickly recombine to form oxygen. The half-life of oxygen is only 20 to 60 minutes depending on the temperature and the humidity, and so it has to be used, and it cannot have the residual chlorine or residual disinfection. And besides, the ozone cannot also be stored or transported. It has to be generated at the site. So this requires feed gas separation and ozone generation equipment. It needs pure oxygen, because if you use air as the source of oxygen for generating ozone, it's not very effective also. So these are some of the disadvantages of the ozone disinfection. And finally comes the selection of the water treatment process and processes. And you'll see that this is the most challenging part of the environmental engineering for water treatment. Selecting the best, the most ideal or the optimum processes is quite challenging. So usually you start with the process diagrams, which is a flowchart of the treatment trains that you're going to establish for the water treatment plant. But while working on your process diagram, it's important to consider the following. First thing is that you need to understand the the characteristics of the source water that you're going to teach, to design. The source water characteristics will include what are the contaminants present in the water. So if you know the detailed characteristics of the water, then you can target what the treatment requires to remove all this, because after all, the objective of the treatment is to remove all these contaminants. If there is no contaminants, there is no treatment required. So first thing you do is do the water analysis, send it to the analysis laboratory, or maybe you can do it yourself if you have the means. Then, and you need to specify what sort of contaminants that you are looking to. So you can look at the drinking water guidelines, and the standards will show what are the parameters that needs to be considered for meeting the drinking water standards. So treatment objective is basically to make the water safe for drinking and to meet the drinking water standard. So sometimes the treatment may also be required on the need of the owner for whom you are designing the water treatment plant. And your past experience with the design will also make a difference in what sort of process you want to lay out. So sometimes, because some water design engineer may have particular preference of one technology, so it can depend on the experience of the designer. And also the process selection, because sometimes there are a range of options available for each technology. So you have to decide which technology you want to adopt for based on the owner's need. And also the compatibility of the process with the existing one, especially if you are trying to upgrade the existing water treatment plant with advanced process or new technologies. You need to see whether this is compatible with the existing plant. And cost consideration, which is also one of the most important aspects of water treatment plant design. There are a range of technologies, very advanced one, but maybe it's expensive. So is it worthwhile to invest such expensive technology? So you'll have to weigh the pros and cons of having expensive technologies. The environmental consideration is one, because some technologies may produce more waste, even though they treat water, but they may produce more waste, and you need to further treat this waste. So that's also environmental concerns. There may be other problem as well, that the technology may require a lot of energy to consume, and that may also contribute to global warming and greenhouse gas emission because of the energy consumption. So there's some of the environmental considerations that you need to take into account. The other important considerations include the availability of the equipment. You don't provide or you don't design the process in such a way that the equipment come from very, very far places where it's not locally available. So locally available equipments are usually preferred. Or even if it's not locally available, it should be easily accessible to such equipment from other countries. So these are some of the considerations you need to take into account. And the personal technical know-how of the people. If the local people doesn't know the technology, then it is a problem, because once you install the water treatment plant, then it can be a problem with operation, maintenance, and troubleshooting. And the energy, of course, I already mentioned. So let's recap of what we have learned from the earlier one, and then to try to apply this process diagram. So let's process train in a water treatment plant, typical water treatment plant. So depending on the water characteristics, sometimes in some cases you may just have to have just chlorination. You don't have to have any filtration, coagulation. That depends on the quality of the water. So if the quality of the water is very clean, then only chlorination is required just to disinfect the water and just supply directly to the people. So this is usually happens in a very small scale in the villages, especially in the villages where the water source is very clean. Maybe it's a very clean stream, or maybe the groundwater is very clean. So when you have that kind of very clean water sources, you just chlorinate and supply it. You don't require other treatment. And maybe you can, if there are some particles of concern, maybe a little bit of suspended solid, if the turbidity is maybe, say for example, between 1 and 5, or something like that, not very high turbidity, but still water is quite clear, then yeah, you can use just simple filtration like sand filtration or coal filtration, and together with chlorination, and you can supply for drinking water purpose. And inline filtration is another one. Say for example, if you this will involve coagulation, inline coagulation, so you don't need mixing or the flocculation. Or the flocculation. So what you do is at the point where in one of the pipelines, the before the filtration, you can just put the coagulation there, coagulant there, and add the coagulant, and then so you may have some kind of mechanism where there will be some turbulence to have a good mixing, and then that mixing can be easily filtered, sent directly to the filtration bed. You don't need a coagulation, no, flocculation tank and the sedimentation tank. So this is called inline filtration design. So there's also another term called direct filtration, and this involves a flocculation step. So you have coagulation and flocculation, but you don't need the sedimentation tank. You just straight away go to the filtration tank and then chlorination, and then straight away for supply. This is usually for also low turbidity water. I think I mentioned it earlier. So if it is less than 20 NTUs of turbidity, then yeah, you can have direct filtration without having a sedimentation unit. But in most treatment plant or conventional treatment plant, all this process will be there. You have a coagulation. You have, because you haven't shown the grid chamber and the screen bar that should be there. Then you have addition of coagulant here, coagulation mixing, rapid mixing, then flocculation, slow mixing, and then you have sedimentation tank, followed by filtration, and then you supply the water. So this is the typical conventional water treatment plant. Now let's talk about the advanced treatment, how it looks like. So advanced treatment is a combination of conventional treatment process with the additional process to remove the extra contaminants. So oxidation may be required if there is a presence of taste and odor in the water. So maybe because of the organic matter present in it, maybe in the gases, maybe such as hydrogen sulfide, methane, or maybe there's a color in it because of the presence of iron and manganese in water. So all this has to remain. So you can have oxidation at the initial stage, maybe oxidation in the form of aeration, or maybe you can have ozonation, even you can have a chlorination, or you can have a potassium permanganate addition. So all this can remove unwanted taste, odor, and color from the water. So you have this coagulation, flocculation, sedimentation, sand filtration, which continued, and you still have problem with the organic dissolved organic matter. Then you can have enhanced oxidation. It's also called advanced oxidation process also. So in this case, you basically target removal of organic matter, dissolved organic matter, and also sometimes you can target other trace contaminants such as maybe insecticide, pesticides, if you think that they are present in the water. So advanced oxidation may be in the form of ozone, maybe hydrogen peroxide addition, or UV, or for a catalysis using titanium dioxide, or maybe it's a combination of sometimes ozone and then peroxide, or peroxide and UV and titanium dioxide. So all this combination can also be form the advanced oxidation process. The advanced oxidation process will sometimes mineralize the organic matter. The organic matter can be converted into carbon dioxide and completely removed from the water. And sometimes you may have, and also if you still have further taste in order, you can have activated carbon at the end of the treatment process. You can to remove the taste in order. So the activated carbon can be the granulated activated carbon or a powder activated carbon, and usually the granulated activated carbon is used for water treatment. So it's usually the activated carbon is kept towards the end of the treatment processes, because if you keep it initially, then the effectiveness will be very poor, because the many other contaminants will compete for surface absorption, and within no time your activated carbon will be saturated. And then finally disinfection, so to remove the bacterial. And then you can have, as we discussed earlier, you can still have, after the disinfection, you need to have some residual chlorine inside the pipeline, so that the reinfection is not does not occur. And this is mentioned in various forms: chlorine, chlorate, chlorine dioxide, ozone, sodium chlorate, UV, etc. Okay, this is another example of an advanced water treatment. So you can have coagulation with the help of the aluminum chloride for removing suspended solids, followed by sedimentation, and then you may have ozonation to remove organic and taste and odor from the water. Then followed by again sedimentation, and then comes the membrane process, nanofiltration. So nanofiltration will also remove the organic matter from the water. So earlier we used this advanced oxidation process. So nanofiltration can also use as a advanced form of oxidation process. And finally disinfection for the bacterial removal. So this is one combination that you can have as an advanced form of water treatment. The another form of advanced water treatment is also using microfiltration instead of sand filtration. You can replace your coagulation. After the coagulation sedimentation, you can do microfiltration followed by nanofiltration and then disinfection. But sometimes you can even avoid the sedimentation and directly send it to microfiltration and then nanofiltration, but it depends on the quality of the water coming from the coagulation. So there are some PDF files that I will be uploading separately in the Canvas. They refer to some of the calculations of the water treatment plant design, the unit design, such as sedimentation tank, the design of the rapid mixing tank, slow mixing tank, sedimentation tank, and the filtration tank, and also some design calculation or disinfection. So please refer to the PDF files separately, and if you have difficulty in understanding, please do contact me, and I'm happy to have online consultation to explain your problem. But yeah, I am not making it into video because those are quite simple calculations that all of you should be able to follow. But yeah, if you have problem, please do let me know. And this ends the video lecture of this session 1. Thank you, and look forward to seeing you in video 2 or session 2.